Alright, now we're looking at number 8. We've got three sets, A, B, and C, that are subsets of the universal set, which are all the positive integers less than 16. You see that A is the prime numbers, B is the factors of 36, C are the multiples of 4. So let's list the elements of each of these sets. So we said A are the prime numbers. Remember, A is a subset of the universal set that only goes positive integers less than 16, meaning 15 will be the last positive integer that we're including. And so A will be the set of elements, prime numbers. Remember we said earlier on prime numbers begin with 2. That is the smallest prime number. And 3 has got only 2 factors, 1 and 3. The next prime number 5, 7, 11, 13, and the next prime number after 13 is 17, which of course is not less than 16, and so now we're done on set A. Set B are the factors of 36. So these are numbers that do divide into 36 without leaving a remainder. So 1, of course, 1 is a factor of every integer. 2, because 36 is even. Does 36 divide 3 evenly? Yes. Does it divide 4 evenly? Yes, goes in exactly 9 times. 5, no, but it does, 6 is a perfect factor, because of course 6 squared equals 36. And then we said that 4 times 9 was 36, and 3 times 12 was 36, and 2 times 18 is 36, and of course 18 I've gotten too big now, haven't I? Because I'm only dealing with numbers that are less than 16, and so this is where I will stop. And set C is the multiples of 4, and so we've got then 4 is the smallest positive integer. That is a multiple of 4. It's 4 times 1. Here's 4 times 2. Here's 4 times 3. And 4 times 4 would be 16, but I have to do only numbers less than 16. And number 4, A intersection B intersection C. That is to say, which numbers in our universe are inside set A and inside set B and inside set C all at the same time. We'll see that, I don't actually see any number that belongs to all three sets at the same time. 4 appears in B, but not in A. 8 appears in neither of them. 12 appears in B, but not A. And I've now exhausted all the possibilities from set C. And so the answer to part 4 would just be the empty set, which you could also notate just with a set of parentheses. Part B, we need to draw a Venn diagram that shows the relationship between these sets. So let's begin with the 3 circles. I'm going to make a little bit of an assumption for a moment here, and I'll assume that we've got overlapping regions all 3 times. Don't forget your rectangle around the outside if you want full marks. I'll label the one on the outside as the universal set, and here's then the subsets A, B, and C. Okay, let's look at A first. Which of these, we know that the middle part is empty, don't we? Because there's nothing that belongs to all 3, we figured out in the previous question. What things inside A also belong to B? Well, we can see that 2 appears in both, 3 appears in both, and that's it. And so 2 and 3 are in the region in which A and B are overlapping, but they're not inside set C, so that's why they go up there. And then we've got, let's think about the things that are overlapping between A and C. In fact, there are no numbers overlapping between A and C, and so this thing is going to remain empty. And so I suppose at this point you could maybe argue that we shouldn't have even drawn C in a manner such that it overlaps set A. But I'm going to let that go. IB is not going to deduct for that, but if you've redrawn it, so that's set A, that's set B, and we said that set C is not overlapping with A, and so maybe you drew something like that for set C, A, B, and C. I think you're still going to end up getting good answers. What about B and C? Is there any overlap? Yeah, we can see that the 4 and the 12 appear in both. So 4 and 12, or on this diagram, B and C overlapping. The 4 and the 12 must go in this region because, of course, nothing belongs to the middle. And now we should be able to place all of the elements that we haven't used yet. So we haven't used the 5, which belongs only to A. We haven't used the 7, the 11, or the 13, which also belong only to A. And then down in set B, we haven't yet used the 1 or the 6 or the 9. And so they must appear only in set B. And lastly, in set C, 4 and 12 we've used already, but 8 has not been used. And in order for me to finish, I need to think about any other positive integers less than 16, which do belong to my universal set, but I haven't yet drawn. I've already got 1, 2, 3, 4, 5, 6, 7, 8, 9 in this diagram, but I haven't yet put 10. 11, 12, 13, 14 is missing, and 15 was missing. And there's the Venn diagram, and I've already done part 2, writing the elements of the sets into the appropriate places on the Venn diagram. Now if you chose to use this model that I'd started already, let's just fill them in so you can see the rest of them. So A had 5, 7, 11, and 13, while C had 8, and B had 1, 6, and 9. And we know that on the outside, we've got only the elements 10, 14, and 15. So this would have been an even better answer. Part C, from the Venn diagram, we need to list the elements that belong to each of the following sets. So we've got A intersection the union of B and C. Alright, let's first think about the union of B and C. That's everything in B with everything in C, right? The union means that we're going to keep everything in both circles. Where is circle A intersecting, overlapping that region that we just indicated of B and C? The only overlapping part is going to be right here, the 2 and the 3. Now let's also do this on our previous diagram. And so we're, sorry, I've gone down a bit too far. So we're looking for A intersection. So what belongs to A and at the same time belongs to either B or C? And we can see this on this diagram, that the only things that belong to set A and at the same time belong to either B or C are going to be the 2 and the 3. So 2 and 3. Now we want to find out what are all of the elements that are not in the intersection, the overlapping region between A and B. So let's look at the overlapping region between A and B. That's only 2, 3. So we've got to list then every single other element because of the not, the complement. So that's 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And number 3, let's take this region that we just found, the A intersection B not, the complement of what was in the overlapping part of A and B, and find out what numbers in this big long set also appear inside set C. Well, when we look at C, we can see that 4, yes, 8, yes, and 12, yes. And so the things that belong to this set that we found out in number 2 and the C of 4, 8, 12 that belong to both are going to be 4, 8, and 12. Alright, let's have a look at the mark scheme and see how we did. And so there's our, whoops, sorry, number 8, not number 7. Okay, there's our Venn diagram. And these are all of the different elements. So 6 prime numbers, 7 different factors, and 3, 4, 8, 12, and then no solution. Let's see if that's the same. Okay. So yeah, 6 prime numbers, 7 factors, 4, 8, 12, and the empty set. Great. You'll notice that IB has said also accept with the elements correctly placed. So IB will not deduct if you drew your circles like this. Although a better solution, the one that they prefer, is where you realize that A and C never intersect. And you can see that they've drawn in all of the elements in the same places as us, including the 15, the 10, and the 14 on the outside. And then part C, there's our 2 and 3, which were overlapping in A and B, and of course there's nothing that belongs to the C as well. And then we've got every element except for 2 and 3, which reside outside this AB overlapping region. And then everything outside, where does it overlap with the things inside C of 4, 8, 12? Of course, it's just the same numbers, 4, 8, 12, because they do appear in both sets. Okay, we've been given a couple of scientific notation numbers, and we need to figure out what do we get when we multiply x by y, because that's what w is equal to. It's equal to x times y. So let's multiply these two values. I've got 2.6 times 10 to the power of 4, and now I'm going to exit my exponent, and I'll multiply this result by 5.0 times 10 to the power of negative 8. Please make sure you use the negative button, not the subtract button. Use the negative button for the exponent. And let's see what we get. 0.0013. Don't forget that we have the 0 in front of the decimal point. Some of you made that mistake on the quiz. There we go. But then the question says that it wants us to express it in scientific notation. Oops, okay, so element of the integers. Look, don't worry about all of this stuff. Just assume that they said express in scientific notation. That means that we want to move the decimal until just after the first non-zero digit. And so you can see that we end up with 1.3. And how many times did I move the decimal? 1, 2, 3 places. And is it a positive or a negative 3? This was a very small number, 0.00, and so it's going to be a negative exponent. Part B. Which of the two following statements about x, y, and w are incorrect? So, is x a natural number? Well, if we rewrote x, 2.6 times 10 to the power of 4, as a regular number, 26,000. This is certainly true. Is y an element of the integers? So let's calculate y by itself. We've got 5.0 times 10 to the power of negative 8. And the calculator doesn't actually really help me out here because it just expresses it in the same notation. So let's think about what's going on with y. It's 5.0 times 10 to the negative 8. You remember how to handle an exponent? If the exponent is negative, we move it to the bottom of a fraction. And so if we're doing 5 times a tiny number like this, or if you like, you can think of it as 5 over 1 times that, we end up with 5 over 10 to the power of 8. That's going to give you some kind of fraction, isn't it? Because we're not going to be able to cancel everything from the bottom with the top. This is just too big. And so we end up with some fractional value. And this one, then, it cannot be an integer. But is y an element of the rational numbers? Can we express y as a fraction? Sure thing, here it is. Of course, it's 5 over, and then we got 8 zeros, so if we move the decimal point 8 times. And if we really, really were obsessive about simplifying fractions, we can cancel a 5 from the top and the bottom, leaving me with only 1 over 2, 20 million, I think. 7 zeros. Alright, so this one is true, and we're only looking for the two false ones, aren't we? Is w, the value of w that we found in part A, is it less than y? So if we rewrote this as a decimal, well, actually, we don't even have to do that. We should be able to compare this to y and realize that because this has got a much more negative exponent, it must represent a smaller number. And so this one is going to be false. W is bigger than y because it doesn't create such a small decimal. We've only moved the decimal 3 places, and this one we moved it 8 places. It's so small. So we've already found the two false ones. We really don't need to continue in the question. But let's just do it quickly. Look, the sum of any two numbers is always going to be a part of the real number set, so that's obviously true. And vi is 1 over w less than x. So imagine doing 1 over your w value that you calculated. Is that less than x? So that's 1 divided by, and let's put it into parentheses so the whole thing is part of the denominator, to the power of negative 3. And that gives us 769. Is that less than x? Well, yeah, we calculated that x was going to be 26,000 when we moved over the decimals. And so this one's true. Clearly the answer is 2 and 4.